Okay, so this is my talk on manipulating the web audio API with custom renderers and JSX. So I'm going to do two things here today. I'm going to provide you with a crash course on web audio, a brief introduction to JSX. I mean, just a show of hands, how many people use React in their day jobs? Okay, so maybe half and half to 2/3, but I do introduce it quite gently, so it's not going to be too crazy. And then, yeah, I'm going to show you how I effectively wrote a custom renderer that can be targeted by JSX for manipulating the web audio API. So let's kick off. Hey, I'm James. I'm a developer who works with a variety of technologies and languages, predominantly C# and JavaScript. I've gained experience at companies like Sky, Channel 4, Net-a-Porter, Trainline, News UK, etc. And I like to contribute to the community via open source software, writing, speaking, as I'm doing now, and mentoring junior developers as well. And I work at our wonderful sponsors, Wildin. We have recently arrived in Manchester, and by recently I mean our office opened in May, and by office I mean myself in a co-working space, but we finally have Alex on board, so we are growing. So hello from all of us. What I should add, we're hiring as well. So yeah, if you want to talk to myself or Emily about that, then just come and grab us afterwards. But enough about that anyway, let's get into the technical details. So foremost, what is the Web Audio API? It's a browser API for creating audio sources to which effects can be applied and thus can be output to the user's sound hardware or an audio buffer. But we're not going to touch upon this too much today. All I'll tell you is that as well as real-time rendering, you can also render to an in-memory buffer specifically for audio, and then the browser can convert this to an MP3 and do all sorts of crazy stuff with it. It's consumed via JavaScript, which is my favorite language, so that's lovely. It's built upon the paradigm of audio nodes. So an audio nodes can be connected to one another to form an audio graph. And audio nodes can represent sources, such as an oscillator which generates a frequency of a certain wave, or it could be an audio sample, for example, an MP3. Effects such as gain that allow you to control, in layman's terms, how loud an output is or how quiet it is. Panning, so going between the left and right speaker in a stereo context. And also audio nodes can represent outputs, typically called destination nodes, so a speaker or the aforementioned audio buffer. And audio nodes expose properties, respectively, that are known as audio parameters. So on an oscillator, this could be a frequency, or on the stereo panner, this could be a pan parameter. And they can be updated with either direct values, so you could set the gain on a gain node to a number of 0.6, or you can schedule the changes via a variety of methods the audio param interface exposes. And all of this is predicated upon an audio context, which permits node creation and is responsible for hardware scheduling and the rendering of the audio graph it represents. Okay, so what I've just done there is I've chucked a whole ton of terminology and words at you. So how does this actually translate to code? What does the API actually look like? Well, let me show you. So foremost, the audio context that I've described, you create it via a globally available constructor called audio context. So you instantiate an audio context. And from said context, you can, so in this example, we're creating an oscillator node, and then we're creating a gain node. And I wouldn't worry about this too much for now, but the reason I have this getTime function is because when you queue parameter changes or when an audio node starts playing, if it's a source node, then you schedule it against this current time property exposed by the context, which is just for hardware scheduling. But once we've created the nodes, we set some properties on the oscillator. So we set its type to a square wave. We set its frequency directly to 200 Hertz initially. But then you can see on the same frequency property, the same frequency property as part of this audio interface, audio param interface, excuse me, we have this method exponential ramp to value at time. And what this will do is within 3 seconds, it will ramp the frequency up to 800 Hertz. And then we have a gain node that's just fixed at 0.2. So a gain node's gain parameter is anything between 0 and 1 of its original volume. And this is just because oscillators are really loud in the browser. And to hook it up, we use the connect method on the source node. So we connect the oscillator to the gain, and then we connect the gain to the audio context destination node, which usually represents the speakers, at least in the majority of contexts. Finally, because oscillator's a source node and we need to kick off the actual playing of this source, we invoke the start method, and then we invoke the stop method, but we schedule the node to actually stop 3 seconds from when it starts. So to perhaps clear this up a little bit more, I have these examples running. So if I move this, I'm in full screen mode, but it should play. I don't need to show you, but it should play out of the speakers. So if I start, so I have this code in a HTML page, and I'm going to open this in the browser. So localhost 88.1/simple. So there we go. We're generating noises in the browser in real time. How cool is that? Okay, so back to the presentation. Here's one more example. So here in the previous example, we were just queuing one node to another and then to another. But audio nodes can accept multiple nodes as their inputs as well, so you can build more complex graphs. So quite similar to the first example, we're instantiating 2 source nodes here, an oscillator and an audio buffer source node. So what you can do is you can take an audio buffer, which you can convert from an array buffer, which is creatable quite in a straightforward manner using the fetch API. And then we're also creating a gain and a stereo panner, so that will pan left to right. And then what we do here is the frequency is constant, so is the gain and so is the pan. And the buffer property, of the buffer source is simply this, a buffer that represents this Yodel MP3 file, which you're going to hear a few times and you're going to love by the time I'm done with this presentation. And then we connect them in a similar way, only we connect the oscillator to the gain and the gain to the stereo panner. But then we also connect the buffer source to the stereo panner. So you can see we have this more complex graph where multiple nodes are going into the stereo panner, and then the stereo panner itself is connected to the destination node. And then we start the buffer node, the buffer source node and the oscillator node as we saw before. So now if I run this example, I mean, it's just beautiful, isn't it? You have this constant sine wave and then an MP3 of someone yodeling. I mean, how can you not love that? Okay, so that is a crash course on the Web Audio API, so congratulations for making it this far. So Web Audio allows us to specify sound sources, manipulate them with a variety of effects, and render and output the result in real time. Additionally, we can do this in the comfort of our browser with JavaScript, which for myself is a big win. And in general, I think the Web Audio API is pretty neat. But building complex audio graphs in an imperative manner can be a bit unwieldy. So admittedly, there are functional programming techniques and abstractions and reusable functions one can write to take away a lot of this tedium. But because I'm a bit of an inquisitive and slightly strange person, I wanted to experiment a bit more beyond that. So what if we could specify audio graphs declaratively, as I've described, but specifically with JSX? Well, what is JSX? So there are some React developers in the room, but here's a very simple React application. So we have this root app component, and this renders a set of elements, a simple DOM subtree, where we have a main element, a title, a paragraph, and we can go on. And then we use the React.DOM.render method to render that React application into the DOM node that's specified as the second parameter. But when we ultimately invoke this in the browser or even in Node, we're actually invoking React.CreateElement under the hood. So JSX is merely a sugar for these method calls so you can see how we have React.CreateElement. We create the main element as the root element of the app component. Null, the second property is props, but we don't have any props in this case. And then the third, well, I say third set of parameters, but the end parameters going forward are the children of that element. But then how do we transform this JSX into calls to React.CreateElement? Well, I'm sure there are multiple ways, but the predominant one that every React developer I know uses and loves because it's a pragmatic approach is with Babel. So Babel is a transpilation platform. I won't go into this too deeply just yet, but we can use a plugin called Transform React JSX. And then we can invoke Babel to take our source code, and for any JSX files, it will transform this JSX into those calls to React.CreateElement we saw in the transpiled code. But can we target other element creators, also known as Pragmas, using Transform React JSX? Well, yes, we can. So Transform React JSX takes some options, and one of these options is Pragma, and this defaults to React.CreateElement. If we're using another JSX compatible framework, or rather a framework that conforms to the same signature of React.CreateElement, we can substitute whatever value we want. So in a real world example that I'll show you, this will be more meaningful, but you can specify anything. So in this case, I just put ruffle. And then if I transpile that same example, you just have calls to this function ruffle, which doesn't resolve to anything, I should clarify, but it just shows you can substitute React.CreateElement with any other Pragma that you want. And that saves you having to write your own compiler and manipulate ASTs and get into all that gnarly stuff, which is quite nice. So how can we use JSX to consume the Web Audio API? How can we bring these two separate concepts into one, and how can one complement the other? Well, I wrote a custom renderer to do this. It's called Wax. It was formerly Web Audio X, and you can see I kind of struggled with the name a bit, so that's kind of the one I stuck with. And what we have here is it is an NPM module. So, well, it's actually transpiled to a common JS module. It has a set of imports that represent the audio nodes as components, but then we also have two functions at the top. So render audio graph is analogous to React DOM.render. And CreateAudioElement is analogous to React.CreateElement, so that's our Pragma. So on the right, I had to wrap this because it was a bit too long. We invoke the render audio graph function, and you can see we're using JSX to specify this audio graph. So we have a root audio graph, and within that we have an oscillator. And the main paradigm of this is within the audio graph, the first child will connect to the next one, and the next to the next one, and so on until it hits the destination. So when we transpile this, because we're specifying our Pragma to be CreateAudioElement, it's a similar story to what we saw with Ruffle and React.CreateElement. So we've got CreateAudioElement specifying the audio graph as a component type, the properties as the second parameter, which you can see in the oscillator creation, and then also children as the nth parameters. So let me actually walk through the code base, and I'll show you some working examples and how this library is actually implemented. Right, so I am going to, so I can actually see what I'm doing, I'm going to try to mirror the screen, and hopefully things don't explode. Okay. Okay, cool. So I think we are there, right? So I want to open, it's still called Web Audio X locally. I'll open the example and then I'll zoom in and we can work out the font size from there. So if I go to the examples, oops, yeah, it's that fun issue when it zooms everything in. So, yep, code, preferences, settings, JSON view all the time, please. Okay, editor dot font size. It's because I have it set here already. So let's try to make that 22. Okay, is that better or would you like it bigger? Okay, cool, let's roll with it. So this is the example I showed you in the slide. However, you may notice this comment at the top with the @JSX, and we're specifying the Pragma name. This is for ESLint, because if we don't specify this and we're using the React plugin for it, then it will complain that CreateAudioElement's unused. So I haven't found a nicer way of managing this within the ESLint config, unfortunately. Maybe you know one, but from what I read, you have to unfortunately mark each file manually. So before we step into the code, I'm going to run this. So entry equals simple. npm run dev. Yeah, you don't have to worry about the terminal output too much. So if I go to localhost 8080, there's that beautiful oscillator again that I know you're all starting to warm to dearly. So let's take a look at this then. So I'll start with my two configs. Foremost, I'll show you my Babel config. So it is also possible to use the React preset directly. That also supports the Pragma option. But in my case, I started with the Transform React JSX plugin directly, and then I added the proposal for the object rest spread because that was quite helpful with destructuring and other things. So I specify the Pragma to be CreateAudioElement, and then in order to build the front-end client bundle for the app I just showed you, I'm using Rollup. And what I've done is effectively, because I have 3 different apps and one common HTML bootloader, it's possible to specify the entry point as an environment variable, or it defaults to simple. And the interesting thing here is, so there is some conditional stuff for if the entry is the React interop example, which we'll get onto later, where it actually imports the, it uses the React plugin, but it specifies this Pragma of CreateElement, and I'll show you how they interop later. But for now, if you don't use the with React application the entry point, if you don't specify that, it will just use the defaults in Babel RC. So if we have a look at the transpiled code, sorry, not for the library, but for the application itself. So, okay, if I scroll to the bottom, so there's our audio tree for our application. So we're creating an audio graph here, and then we're setting its children, which also resolve to CreateAudioElement, having been transpiled from JSX, and so on and so forth. But now I've mentioned CreateAudioElement about 1 million times, I bet you're wondering, what does CreateAudioElement do? Well, let's step into the library and I'll answer that question for you. So, CreateAudioElement. So, what this does is foremost, it has a signature of components, props, and children. So this is completely compatible with React.CreateElement. And then what we do within that is, I should show you the render entry point actually. So what happens here is in render audio graph, we invoke So when a CreateAudioElement is invoked in our code, we're returning a function. And in order to get the nodes, this is the function that's returned from said function, where we're passing the audio context to it. So if we step into CreateAudioElement, that's this inner function here. Now, I won't go into what the node tree is, apart from it's a multi-dimensional array right now. But effectively, what we do here is we take the component we're trying to render, which is the first argument, into CreateAudioElement, and then we pass it some props. And an example of a component is, let's have a look at Oscillator. So this is the component that we're rendering using JSX or CreateAudioElement in order to create a new oscillator node. So very much like a React component, or in my library, by the way, all of these are stateless. I don't support class-based components because I didn't have a need for them at the time, but that's something I could introduce later on. Effectively, what happens in React is we're taking props in and we're returning React elements out. In my case, we are taking props in and we're returning an audio node that we've either created or has been reconciled. So in our case, if I go back to the example again, so here we have the oscillator element instance, and we're passing it props such as frequency, the type, and when it should end. So if I jump back into Oscillator, so these properties we've specified in our app map to these properties here. And we assign the detune property to the nodes detune property, and so on. And then we enqueue it for playback. So there are two things that might stand out to you here. The first is this assign audio param, and the second is this mystical enqueue function we're receiving as a prop. So let me begin with assign audio param. So if we go back to the source again, I appreciate we're doing a lot of jumping. So here for the frequency, what my library allows you to do is specify a chain of operations as an array. You can either give it a direct value, as we're doing with gain node. You can give it a single one of these mutations that's not in an array, or you can give it an array and it will apply these mutations in order. So this resolves in the oscillator node to this call to assign audio param. And what assign audio param does, if I can find it, yeah, param mutations. So what assign audio param does is, so I'll show you actually what the mutations look like. So set value at time, linear ramp to value, etc. They all follow the same signature. So rather than duplicate a lot of the boilerplate over and over, I just have this helper function called CreateParamMutator. And what that will do is it will take a value and a time, and then it will return this function, and that's called by assign audio param. So in this case, if we go back to the example again, the first one, set value at time to 200 Hertz, and we're setting that immediately. So these are going to be received by this inner function, the first inner function, and that itself returns another function, talk about partial application. And then what happens here is in assign audio param, we have the param, the value, and the current time. Foremost, if there's no value, we just return. If it's a single mutation, so if it's not an array but it's a call to say set value at time, then we invoke that inner function with the audio param directly. So as you saw in the initial examples, we're setting the pan on stereo pan_node.pan.value. Pan in that case is the audio node. So this instance of that param is received here with the current time, the scheduling. or if it's a sequence like the array, then it's pretty much the same thing, but we're just applying it in order for each element. Or if it's a direct value like in the gain node, we just set it to, I think it was 0.2, then we just set the value property of that param directly. So it's just a means of aggregating that logic into one place. And then the other interesting thing here is this enqueue. So because we have multiple source nodes like Audiobuffer source node and Oscillator node, I found there was more boilerplate being repeated where you start the node, and if there's an end time prop, then you conditionally stop the node for that scheduled time. So what I decided to do was write this higher order component, so as source node. And what as source node does is it takes the component, or the component type. In this case, it takes it actually takes the component creation function. So that will take Oscillator, and then that returns a new component, which is props. So what happens here is we render the Oscillator, in our case, and as well as respecting the props that were passed to it by the consumer, we also inject the enqueue function. And what this will do is it will do things like, if it's scheduled, say you've re-rendered or reconciled, don't start it again because you can't start an audio node more than once. Or you start it, and if there's an end time param, then you schedule it to stop at that time. So I just didn't want to repeat this logic over and over, and I thought that consequently a higher order function would be the appropriate way of composing and showing that logic. And yeah, if we go back to the oscillator, then yeah, we invoke the enqueue method with the node we've created. So I'll show you a second example. So that's aggregation. So there are some cases where what we might want to do is, like in the second example, we had an oscillator, we had an audio buffer source, and I think the oscillator was connected to a gain, not the stereo panner, but I think the buffer source and the stereo panner ultimately ended up at the same node. So an aggregation mimics that. It's a little bit of a hack, I'm not going to lie. I like to call it a workaround, but it's a bit of a hack, and it is a limitation of this approach I've taken. So what an aggregation will do is, what we're doing here is we're fetching Yodel as an audio buffer. I'll give you the context actually. So I've mentioned audio buffer quite a bit. So we can use the fetch API to fetch a resource and convert it to, or rather expose it as an array buffer. And then we can pass that array buffer to the decode audio data method of our audio context, and that will create an audio buffer that can then be manipulated by audio buffer source node and a variety of other means. So we get that as an audio buffer, and then how our aggregation works is we create a standalone stereo panner instance as so, and then an aggregation in my library works like an audio graph. So it will go through the nodes in order and it will connect one to the other. So it will connect oscillator to gain and gain to stereo panner. But in the outer graph, if it's an aggregation, it won't try to connect an aggregation to an aggregation. I just resolve that to a no-op, and that's ignored by the node reconciler. And then, so those two aggregations are connected to the stereo panner, and then the stereo panner is connected to the audio context destination. So if I run the aggregation example for you, so it's like the other example I showed you, another Yodel, another, I think it's a square wave in this case. So we can still compose more complex audio graphs using JSX in this componentized manner. What else can I show you? And render audio graph as well. So just to reiterate what that does, and then I'll go into the React interop. So render audio graph. So what this does, yeah, of course, I haven't shown you the code that connects the actual nodes together. That might be useful, right? So we create the graph, we actually invoke all of the element creation functions, and we get a multi-dimensional array of audio nodes back. And then these are connected by the connect nodes function. So what we do here is we take the array of nodes and we reduce them. So we start off with a source node and a target node, so typically it's the first and the second. If it's a nested array of audio nodes, either the source or the target node, say it's like an aggregation and you've got children of children, then we merely flatten the array out, so it's just one array in order. And then if it's not a no-op node, which is the last node returned by our aggregation component, then we connect each source to each target, and then we return the target. So because of how array.prototype.reduce works, when we return target here, then source node will next resolve to what was the target node. So you can chain one to the other and then to the other and so on in this manner. So that's obviously a whirlwind tour of this fairly complex code base, but that is essentially how this works. And there's one more thing we need to cover. So what if we want to bring this into a React project? What if we want a componentized UI driven by React, but then we want to control and manipulate an audio graph as a result? Is it possible to combine these two things? Well, yes, it is. So I'll show you that too. So we have this example with React. So foremost, the Pragma is just this mysterious create element. And we import the React and React DOM libraries. And then I import my own library as well. And I've written this helper called combine element creators. And what happens is you pass it a mapping of firstly a predicate that will tell you if a certain component belongs to a certain library or renderer, and if it satisfies that condition, then it will use that element creation function. Or in this case, by default, we just return react.createElement. So how combine element creators works is we take the creator bindings, we convert them into a map, and for a component, props and children, so this is the outer signature we're exposing again, we get the creator for a particular component type, and if it satisfies that predicate, we return that creator. So in our case, just to clarify, if it's a component of my library, we use CreateAudioElement, otherwise we use React.createElement. So onto the components themselves. So I have this slider component where, actually no, I'll show you the actual rendering first. So we use react.dom.render to render the actual component tree. So we have this slider component, that's just an input with a type range. And then I have a render prop, and when this changes, this is invoked with the value of that slider. And from that I return an audio graph tree, and the oscillator will take that value as its frequency. So if I show you how slider is implemented, so when the component did mount lifecycle method is invoked, so that's after first render as well, it will render the audio graph only with this second function called render persistent audio graph. And this will have fed to it the return value of this.props.children, the render prop, and we just pass the minimum value for now. And then when this changes, we invoke the same render prop again, but with the updated value. I've just missed a key part actually. We don't call render persistent audio graph again. Render persistent audio graph returns a function you call to then subsequently update the audio graph without destroying the existing node you have or the existing tree. So you call update audio graph, you pass it the same graph, and it will attempt to reconcile the updates with the existing graph you have. So I'll show you the example and I'll show you how the reconciliation works. So with React, and if you love the yodeling and the increasing frequencies of the oscillator nodes, you're going to love this example. It's not going to annoy you at all. I almost felt like a child when I was writing this. It's like I can really annoy my parents and my family with this. So we have a constant node. God, I'm having so much fun with this. I don't want to stop, really. So the idea is, what would happen is if we use RenderAudioGraph here, because we're not trying to reconcile the existing tree in any way, we keep creating new nodes, and rather than having the frequency change, you'd have a new oscillator with the updated frequency, so you just have like loads playing at the same time, and it sounds like if you were to lean onto like a church organ. It's even worse than that. So how does reconciliation work? Well, unfortunately, I didn't have as much time as I would have liked to get this working properly. So in React, you can do things like conditionally insert elements. It doesn't handle those diffing cases that well, it doesn't handle them at all, unfortunately. So this is still a work in progress. I'll show you what I have now nonetheless. So what render persistent audiograph does is it exposes the same contract as RenderAudioGraph. It will do the initial render and return the audio nodes, and then it will return a function that one invokes to update the audio graph. So what this will do is it will take the same tree, but then, well, it will take a new tree actually, because it will have the value update on the oscillator, but then it will take the existing nodes and it will recursively traverse that tree, take the nodes that already exist, and feed them into the component function. So let me show you that. So in CreateAudioElement, so you might remember I mentioned audio tree and not to worry about it for now. Well, this is the time to worry about it. So when I say a tree, it's a really glorified term for a multi-dimensional array. And what we do here is we pass the existing multi-dimensional array of audio nodes that we have, and we just assume a one-to-one mapping. So we assume the tree hasn't changed, which is a limitation. We should be reconciling that properly, diffing which nodes and elements have been removed, and like reconnecting the gaps as a result. My initial implementation, all it will do is it will take this node tree, assume that the oscillator at this position corresponds to the same oscillator node that already exists. And then this existing node gets passed into the component function. So if we go back to Oscillator, how this works is if the node isn't provided with a value, then it defaults to creating a new oscillator, and then it's returned, so it's props in audio nodes out. But we already have an audio node in our reconciliation, so we don't recreate it again. We just use the same reference, update that one, and then return it back, and so on as we adjust the slider and continue to update. So really, I should be using a proper tree for this, diffing the nodes that have been added or removed, and then reconnecting those and maintaining state somewhere, but that's for another time. Okay, so if I stop mirroring my displays now, and if I get the presentation back up and not open Safari accidentally, where did it go? Oh, I closed it. Brilliant. Right, okay, so let's just get this back up. No, I don't want it on this screen. So, summary. Okay. And view, present. Okay, cool, there we go. So, to summarize all of that, web audio is an amazing capability. I mean, real-time sound generation in the browser, that's pretty awesome. I mean, the web has come such a long way, and this is really a testament to that. The audio graph model is logical for composing complex audio graphs. Like, I have no problem with its structure, and I think it was the right design choice, without a doubt. But the imperative connection code can be tedious. Again, as I said, there are more functional and declarative ways to handle that outside of my example. But componentization with JSX and a custom renderer, it certainly helps us from a consumer's point of view. But reconciliation and interop, as I've just discussed, are hard, and they're not the kind of thing you can do in one evening like I try to do. And, oh no, my thinking face emoji hasn't appeared. That was the one right at the end that didn't appear. Bloody Unicode, hey? But it's fine, that's supposed to be a thinking face emoji. Is JSX for web audio overkill? I mean, this has been an interesting experiment, and perhaps there are some limitations and things I need to weigh up and ultimately productionize it further. But it's definitely a pertinent question, and it depends upon developer familiarity and what one's trying to achieve ultimately. Okay, thank you for listening. I'm more than happy to take any questions. Oh, I should say also, I'll tweet this out, but the slides and the repository are publicly accessible. Okay, thank you very much.
Well, thank you, James. Do you have any questions for James?
Cool, that's right. So for the frequency, you pass those mutators through, you change the frequency and ramp up.
Yep.
Can you do that for any sort of parameter?
Yes, exactly. So the point, well actually it depends upon the implementation. One of the limitations I am seeing, and that's an interesting question you've raised, if I exit the presentation and I'll bring the code back. So of course in, that's not the one I wanted, that's the one I wanted. Right, so in Oscillator I'm still having to specify these mappings manually, or if it's not an audio param, I'm still having to set the type manually, so there is that work involved for each component type. I haven't implemented all of the component to node mappings, I should add as well, that's a work in progress. But yeah, how the, as you know, if I specify this call site here, then yeah, that can be any of those param mutators because they all conform to that same contract. And yeah, when you set a value, it's all based upon time, so set value at time, exponential ramp to value at time, set to target at time, which is, sorry, I think it's set target value at time when you're aiming to get to a value within a certain time. You don't have to hit it like exponential or linear ramp to value. But the idea is because they're based upon a value and time, that contract is consistent. So because of how I'm creating the param mutations here, it's one reusable function, and I use this same creation factory just to create the same mutators, and they just work across the board.
Could you get the YOLO through RAM?
Well, you have things like channel merger and channel splitter, which handle like multiple channels. I think, no, that's it. There's, as well as stereo panner, there's a panner node as well. I couldn't get my head around it. It's a bit too complex for my small brain, but the idea is it will support like surround sound and like spatial stuff, so that capability is there for sure. Cool, thank you. Any other questions?
So, when you set up those audio sources, those sounds just play at the same time, or can you like put it into a timeline, like play one after each other?
Yeah, absolutely. I mean, I haven't written any kind of declarative functionality to handle that, but if I go to one of the examples, if I go to aggregation, right? What I could do is, it's the audio buffer source node. So what I could do is I could set the, I think it's start time prop to, so you don't have to worry about the scheduling with the current time as a consumer, you just specify the time in seconds from rendering effectively. So I could say start time equals 2 seconds, for example, and what we will have is, if, hopefully anyway, if I start this, so it's the aggregation example. Okay, and if I go back to do, I have it open? No, that's fine. Yeah, I'm using node static and there's some weird caching, so I'll have to do a hard refresh. So you can defer in that way for sure. That's an interesting question because there could be some really nice means of expressing like sequences of source nodes beginning and ending in a non-imperative manner, and I think that's quite cool. So that's one to consider. Good question. Okay, anything else, or is that a wrap?
Cool. Well, thanks again.
Yeah, cool. Thank you.